Hello everybody and welcome to your AP Daily video. This video is about what you're going to be doing in class today, 1-6. And like I said, I'm going to be going over what you need to do today, plus a few extra things that I was planning to go over with you in class. My name is Tucker Basil from Chaska High School in Chaska, Minnesota, and I'm proud to say I'm here with the high school plank. So here we go. First thing that I want to talk about with you is what to know about steady state approximation, which is, I don't know, the next learning target that you're needed to take notes on for class today. And so I'm just going to hit the highlights. Again, not everything is going to be everything that you need to know for this, but it is what you need to know, but not everything that you need in order to learn this topic. So first, remember, the slow step is the rate determining step. You make the rate law from the slow step using only the reactants, because the slow step is the thing that's kind of like the bottleneck that's going to hold up all of the series of events that end up in the overall reaction happening. And it's only the reactants because the reactants are the things that are actually physically colliding with each other to form the new substances. But that can sometimes be a problem. Because we do not want intermediates in the overall rate law. Catalysts are okay because they actually do influence the rate. But yeah, we just never want intermediates. And because we don't want intermediates, and if you don't have the slow step being the first step, you can have some problems. So many times the slow step is not the first step, so you end up with an issue because of those intermediates, like I was saying. So here's a proposed mechanism. If step 1 is the slow step, which it would say off to the right hand side, there's no intermediate in the reactants, so you just make the rate law based off of what you see here. So the rate would be K1 times the concentration of NO2 times the concentration of F2. And keep in mind that I'm just tossing these subscripts on here based off of the step that it's in. So K1 is just the forward reaction for step 1. The subscript isn't super important, but you do have different K values for each of the different steps. If you went forward or reverse, you would have a different rate constant as well. So that's all that, just be aware of that, I guess. But if I have this step 2 as my slow step, it says it off to the side, you end up with a problem, because if you were to write your rate law based off of step 2's reactants, you'd end up with fluorine as an intermediate in the overall rate law. And it's an intermediate because it's made in one step and then consumed in the other. It's not present before or after the reaction takes place. That's exactly what I just said, so I don't think I need to repeat myself. But yeah, we do not want to have fluorine in the overall rate law. So what you do is you use the previous step, so in this case step 1, to set up an equation so you can substitute in any non-intermediates. So that would look like this. Well, before we do that, keep in mind, since this goes fast, we can say that the rate forward equals the rate reversed. But we have to use a different K value because all reactions have different K values. And so we could set up an expression that looks like this, where K1 times NO2 times F2 equals the reverse of that. So I just call that -1. Again, the subscripts aren't super important, but they need to be different to remind ourselves that there are different K values. Times the concentration NO2 and F. So I got this by doing the rate law for these here. So assuming that this is going forward, I get NO2, that's where this is coming from, and F2 is where that's coming from as well. Now if you could imagine flipping this around and having these be my reactants and these being my products, I would end up with the rate law being the concentration of NO2F, that's this here, and F, that's where that is coming from as well. And then again, it's step 1, but it's in the reverse direction, so I don't know, call it a -1. Call it subscript banana, doesn't matter to me, but to me, calling this a -1 makes sense because it's step 1, just going in the reverse direction. Yeah, and they're equal because it's the rate forward equals the rate reversed. So now what we need to do is we need to solve this for F and we're going to substitute that in to the rate law that we want to have for the slow step here. Okay, and if this works out the way it should, we would end up with no intermediates in the overall rate law. And so I'd end up with, I want to divide, so I'm solving this for f. So I want to divide K, sub -1 and the concentration NO2F to the other side. So I end up with K1, NO2, and F2 on the top, and then these guys right here on the bottom. Okay, hopefully you can see that. And so then, if you write this in the way that you would want to write your rate laws, because, this is the same as this over here, but it's best practice to write it all in one line. So having K1 divided by K sub -1 times the concentration NO2 times F2, and then we just make this to the -1 power. And that would be our overall rate law for this if step 2 is the slow step. Whew, there you go. So you're definitely going to want to practice this. So that's going to be one of the things that you're going to do in class today if you're all caught up on things. All right. Let me move my floating head down here a little bit. What to know about multi-step reaction energy profiles. Whew, and I kind of touched on this already, but multi-step reaction energy profiles, multi-step, it's just 2 steps, reaction energy profile. It's just the energy graph thing. So multi-bump energy graph thingies is another way to say that. So each peak corresponds to a different step in the mechanism. Egads, Batman. You've got to be kidding me. Yeah, that's it. And then the slow step is the tallest peak. So you can see this here, that this would represent a multi-step mechanism, where this would be the first step, this would be the second step, and then this one would be the slow step, which would also be the rate determining step. And that's all you really need to know about this. You have to also be able to draw these if, when it comes time for that. All right, and then lastly, what do you need to know about catalysts? Well, let me move there. You need to know what is happening when a catalyst speeds up a reaction. So it's one thing to just say catalysts speed up reactions, but it's another thing completely to be able to explain at the particle level what's actually physically happening. So, if let's say you have an FRQ that has a part that says what's actually happening when this reaction is catalyzed or has a catalyst that's being used. It forms a lower or more stable intermediate, which would change the peak in your reaction energy profile, and it does this by making the collisions more effective. So it's helping more collisions take place, because if there's more collisions taking place, there's a higher likelihood that a reaction would take place, or it's making the collisions so that way they're in a better orientation. And so both of those are different ways that a catalyst could actually physically help that happen. So there you go. That's really what you need to know about catalysts. There's more details to it than that, but that's kind of the big takeaway from that learning target. So here is your thing to do today. So here are the things that were due before. You can read that. I don't think I need to read that out loud to you. Let's see, I'll move there you go. Now my head's over the one that says Cheerio. That's great. Oh, now it's T2IL. Now it's okay, love you, bye. Anyways. Okay, so Cheerio. And here's what you need to do today. Do the rest of the chill. I don't have it open in front of me. I think it's pages 14 and 15, but basically it's the rest after you're done with 12 and 13. Make sure you look at the videos that it says to do for those, and then fill out, the questions either digitally or in your notebook. So that way you can help your future self when it comes time to study. Do the last section in the textbook. It's about catalysts. It goes a little bit beyond what you need to know for this class, but you actually might find it interesting to learn about enzymes and how a catalytic converter works in a car to do things. It's cool. Read it, really do. It's great. Then do practice number 4. I will be posting that in Google Classroom for you. And then heads up, your test is next week, and then you'll be having a quiz on all the, second half of this unit, so like mechanisms and more, soon. All right. Ooh, I almost signed off. Gotta have a joke break at the end of the video. So here you go. Here's your joke. Why did the white bear dissolve in water? Because it was a polar bear. Gotcha. All right. Thank you, and see you next time.